Welcome to this deep dive into perception-informed neural networks. We're about to explore a really interesting new frontier in AI.
Absolutely.
Now, we were hoping to have Dr. Mazandarani with us, one of the key minds behind this research.
Yeah, that would have been great.
Unfortunately, he's traveling right now, so we couldn't quite make the schedules work. But no worries.
No, we can still cover it.
We're definitely still going to unpack his fascinating work on these perception-informed neural networks. So what are we actually looking at today?
You, the learner, have flagged some really interesting stuff about a new wave in artificial intelligence.
That's right. Yeah, we're jumping into perception-informed neural networks, or PRINs, as they're called.
PRINs, okay.
Think of it as an evolution of something you might have heard of before. Physics-informed neural networks. PINs.
Okay, let's unpack this then. So instead of just feeding AI tons and tons of data like usual, we're looking at a way for it to maybe understand the world more like we do.
Yeah, exactly. By incorporating our knowledge and, well, even our uncertainty about things.
And this builds on that foundation of PNNs you mentioned.
Precisely. Physics-informed neural networks, the PNNs, they were a really significant step. They showed us how to integrate known physics, often expressed as mathematical equations, directly into how a neural network actually learns. But PRINs, they take a much wider view. So our goal today is really to explore how this new framework lets AI model systems, even when the, let's say, precise physics isn't totally nailed down.
Okay.
And crucially, how it factors in this idea of human-like perception.
That sounds like a real leap forward. I mean, the research you shared talks about PRINs handling perception in all sorts of ways, like single numbers, probabilities, even these things called fuzzy graphs. It almost sounds like teaching AI to understand that things aren't always so clear-cut,
Precisely. Yeah, this ability to work with different kinds of precision, as the paper calls it, is what makes PRINs so versatile.
Perception precision.
It allows us to represent uncertainty in ways that, well, traditional AI often just can't.
So think about how we work. When we try to understand the universe, we usually start with how we see and experience things, right? Our perceptions.
That's a key point. Yeah, our perceptions lead to experiments, maybe observations, and eventually we might formalize those into mathematical laws like we see in physics.
Think about gravity, maybe. People saw things falling for ages before Newton gave us the math for it.
Exactly. A perfect example. He formalized that perceived force.
And traditional AI, it learns about our perceptions, but kind of indirectly, by analyzing just massive amounts of numerical data.
Correct. The more data, the better it gets at mirroring our understanding of the world, essentially.
But it's learning through the numbers.
Right. These data-driven models are incredibly powerful, don't get me wrong, but they're essentially learning our perceptions through the lens of measurements. And that numerical data, well, it doesn't always capture the nuances of how we actually perceive things.
Which brings us, I guess, to the central questions that PRINs seem to be tackling. Can we directly tell these networks what we perceive, but in different ways, not just numbers? And can AI develop a useful understanding even when hard data is scarce?
Yeah, these are the core challenges. And physics-informed neural networks, PNNs, were kind of an early attempt to address this. The idea was, okay, we have data, yes, but we also have these well-established physics principles. Let's inform the network with those too.
All right. And the crucial part of PNNs, as I understand it, is embedding those physics principles often as differential equations. Those rules describing change directly into the network's learning process.
Exactly. It becomes part of what the network tries to get right.
So it's not just matching data points.
No. These differential equations are integrated into what's called the network's loss function.
The loss function. That's like the network's score, right? How well it's doing.
Pretty much, yeah. Think of it as its report card. In PNNs, that report card doesn't just look at how well the network matches the data, but also how well it adheres to the known laws of physics.
That makes a lot of sense. So when are PNNs particularly helpful? Can you give some situations where they really shine?
Sure. Well, first, maybe when you don't have a lot of direct measurements, but you have a pretty good grasp of the underlying physics described by those differential equations. The PINN can use those physics laws to make, let's say, educated guesses where the data is missing.
Right, fills in the gaps.
Exactly. Second, maybe you have some data and you know the general structure of the equations governing the system, but some specific numbers within those equations are unknown, like a parameter maybe.
Oh, yeah.
The PINN can learn the system's behavior from the data and at the same time actually figure out those unknown numbers, those parameters.
That's clever. So it's doing discovery too.
Precisely. Parameter estimation. And third, maybe even if you have limited data and you understand the fundamental physics, but you haven't quite translated it into neat, perfect differential equations yet. The PINN can learn from both the sparse data you do have and the general physics principles you provide it.
Okay, so PINs are clearly a significant step. But the research points out a limitation. They primarily deal with crisp differential equations. Everything is treated as certain. No room for ambiguity.
That's right. The starting conditions, the boundaries, the parameters within the equations, they're all assumed to be fixed, exact values. But, in reality, things are rarely that cut and dried.
Yeah, uncertainty is everywhere. Just trying to measure anything precisely.
Yeah.
There's always some degree of error, right?
Always.
Even fundamental constants like g for gravity can vary slightly depending on where you are.
Absolutely. And think about it, there are many, many systems, especially when you move beyond classical physics into areas like, say, economics or social dynamics, where clear, precise differential equations just don't really exist, or at least we haven't found them yet.
Or even when we do have physics-based models, they're often simplifications, aren't they?
Yeah.
We have to leave out details because they're too complex, or maybe we don't even know about them. Unknown factors.
Exactly. And this is where incorporating human perception becomes crucial again. Experts in a field often have really valuable intuition, a kind of gut feeling for how a system might behave, even if they can't express it with a perfect equation.
Yeah.
And crucially, how they understand the uncertainty involved can differ. One expert might say a certain value is around 5, maybe thinking of a range like 4 to 6.
Okay, and interval.
Right. While another expert might think of it as a probability, with 5 being the most likely value, but other nearby values also possible.
A distribution.
Okay.
Same parameter, different views on the uncertainty.
Exactly. So PINs, relying as they do on these precise equations, can't really capture that kind of fuzzy, uncertain, sometimes subjective knowledge very well.
And that's the gap PINs are trying to fill.
That's precisely where perception-informed neural networks come into play. PIN are designed to directly integrate these perceptions, whether through language, through statements, propositions, or through what the research calls imprecise differential equations, IDEs.
Imprecise differential equations. IDEs. That almost sounds like a contradiction. Differential equations are usually pretty precise things.
It might seem that way, but it's actually a really powerful idea. And PRINs don't replace PINs. They really see PINs as just one specific approach within a much broader framework for informed AI.
Okay, so how do PRINs actually do that? How do they take these somewhat vague human perceptions and make them useful for a neural network?
The key concept is a process called precision.
Precision, right. You mentioned that.
Yeah. It's about taking those imprecise perceptions, often expressed in natural language words, and transforming them into something more structured. Generalized constraints, or GCs.
Generalized constraints. Okay, that sounds pretty technical. What does it actually mean in practice?
Think of a GC as a kind of flexible boundary or guideline for a variable or a parameter, or maybe the state of the system itself. It's not necessarily a hard rule, but rather a constraint that has a specific mode of precision.
A mode?
Yeah, the mode tells us how that imprecision or perception is being represented mathematically. And like we touched on earlier, this could be a single number, the singular mode, like in PNs, where there's effectively no imprecision represented.
Okay, the crisp case.
Right. Or it could be a probability distribution showing the likelihood of different values, or a possibility distribution indicating what's plausible versus implausible, or an interval representing a range, like that 4 to 6 fin example, or even a fuzzy graph, which can capture more complex fuzzy relationships.
Wow. Okay, so it's a whole toolkit for representing uncertainty. Can you give a concrete example of this precision in action?
Sure. Let's say an expert observes the system and says, the variable y changes quite rapidly with time when the time is around 10 seconds.
Okay, vague but informative.
Right. A PRINN, using precision, could translate this into, say, a probabilistic generalized constraint. This would mean that the rate of change of y, its derivative, at times close to 10 seconds, is likely to be within a certain range of high values, defined by a probability distribution.
I see. So instead of just a vague statement, the network gets a mathematical representation of the likelihood of different rapid changes around that time.
Exactly. Now, when we apply this to dynamical systems, those systems that change over time, we're often dealing with either imprecise descriptions of the system itself, maybe in the form of these IDEs we mentioned.
Right, imprecise differential equations.
Or we have experts giving us descriptions or opinions about the system or parts of it, as these natural language propositions like the example I just gave.
Let's dive a bit deeper into these IDEs, the imprecise differential equations. How are they fundamentally different from the standard ones we use in physics?
Well, in a standard differential equation, all the components, the parameters, the initial conditions, the boundary conditions, they're all defined with exact numerical values.
Crisp numbers.
Crisp numbers. In an IDE, however, some of these components are described using propositions which inherently carry imprecision. Think back to maybe a damped spring, an oscillator. A standard equation would give you a precise value for the spring constant, the damping ratio. An IDE might instead incorporate statements like, the spring is quite stiff, or the damping is somewhere between low and moderate.
Ah, okay. So instead of saying stiffness equals exactly, say, 10.5, we're giving it a more descriptive, less precise characterization based on perception.
Precisely. These IDEs represent a mathematical description of a system that explicitly incorporates our inherent imprecision or perception in how we understand or describe it. The research even talks about the underlying mathematics as perception-based calculus.
Perception-based calculus.
It's a calculus of impression, if you will.
I like that, the calculus of impression. So if we have one of these IDEs with these fuzzy descriptions, how do we actually get a solution out of it? How does the AI work with that imprecision?
Right. That's where the precision step becomes absolutely crucial again. To actually solve an IDE, or rather use it to inform the network, those imprecise propositions need to be converted or precisated into a specific mode within that generalized constraint framework we talked about. Now, if we choose to precisate everything in the singular mode, meaning we basically decide to treat those approximate or fuzzy values as if they were exact single numbers.
We just pick a number.
Essentially, yes. Or assume the description points to one specific number. Then our IDE effectively collapses back into a standard, crisp differential equation, the kind that traditional PNNs are designed to handle.
Okay, so using singular precision brings us back to the familiar PNN territory. That makes sense.
Yeah.
But what happens if we use these other modes of precision, like probabilities or possibilities or intervals?
Well then things get more interesting. Then we end up with what are generally called uncertain differential equations, or UDEs.
UDEs, okay.
So if we use intervals to preciate our imprecise values, we get interval differential equations. If we use probability distributions, we get random or stochastic differential equations. Possibility distributions lead to fuzzy differential equations.
So the way we choose to represent our uncertainty mathematically directly determines the type of mathematical equation the network ends up working with.
Exactly. That's a key advantage of the NEN framework. It can handle a much broader range of mathematical descriptions, ones that can better reflect real-world uncertainty and perception.
So the choice of how we formalize our uncertainty, our perception, has a direct impact on the kind of equation the network is learning from, and ultimately the kind of solution or prediction we get out.
Absolutely. And the research calls the solution you get after applying a specific mode of precision the precisated modal solution of the IDE.
Precisated modal solution.
Yeah. It's the output, but now it inherently reflects the specific type of uncertainty we initially incorporated through our chosen precision mode. It's important, though, to distinguish this from the sort of conceptual modal solution of the IDE itself, which exists at the level of our initial imprecise statements, our perceptions, not necessarily tied directly to measurement-based quantities yet.
This is really fascinating. The idea of AI being able to reason and make predictions while acknowledging and actively working with the same kind of inherent uncertainty that we humans grapple with.
But wait, it gets even more interesting when you consider that different experts might have different ways of understanding and quantifying the same uncertainty.
Oh, right. We talked about that. One expert sees an interval, another sees a probability distribution for the same parameter.
Exactly. So even the experts might not see eye to eye on exactly how uncertain something is or what kind of uncertainty it is.
So how do PRINs deal with those potentially conflicting perspectives?
That's handled through a concept called mixture of experts, or MOE precisation.
Mixture of experts, okay.
Here, the IDE isn't just precisated based on a single expert's view or a single chosen mode. Instead, it uses a combination of different experts' opinions on the most appropriate mode or modes of precisation.
So you blend their views.
Sort of, yeah. This leads to what are called MOE-based differential equations. The network can learn from a blend of different ways of representing uncertainty, reflecting the diverse expert opinions.
I see.
The real power here is that PRINs, through MOE, can potentially reconcile or at least incorporate these differing expert opinions on uncertainty. This could lead to a more robust and nuanced understanding than if we just sort of picked one expert's approach and ignored the others.
So instead of just one type of equation reflecting a single viewpoint on uncertainty, we might end up with like a collection of different types of equations or a hybrid equation, each representing a different expert's perspective.
Precisely. For instance, going back to our damped oscillator example, if one expert thinks the natural frequency is best described by a probability distribution, while another believes a possibility distribution is more appropriate for the damping ratio,
Okay.
the MOE precisiation could lead to a kind of hybrid differential equation that incorporates both randomness and fuzziness. The research even mentions specific types, like Z differential equations, as an example that combines both fuzzy and random elements.
Z differential equations.
Ah.
Wow, okay. Sounds like we're venturing into some pretty advanced mathematical territory here.
You could say that. And this ability to blend different types of uncertainty allows PRINs to be sureness informed.
Sureness informed.
Yeah, meaning they can understand and leverage the logical relationship between something being impossible related to possibility and it therefore having to be improbable related to probability. This kind of consensus or interplay across different ways of perceiving uncertainty can lead to specific network types like sureness-informed neural networks or SNITs.
So the network isn't just learning from the data and maybe some imprecise physics, but it's also learning from the degree of agreement or maybe disagreement in how different experts perceive those imprecisions.
Exactly, and this is a core idea behind another concept mentioned. Transformed Knowledge-Informed Neural Networks, or TKNNs.
TKNNs, okay, yet another acronym.
Ah, yes. TKINNs go beyond just incorporating different expert views. They actually try to look at the meta-information that arises from the interaction of that knowledge.
Meta-information, like what?
Things like the level of agreement or compatibility between different experts' precisiations, or perhaps how confident they are in their assessments.
So not just what the experts believe, but maybe how strongly they believe it and how well their beliefs align with others.
Precisely. The research even discusses concepts like sureness time, which sounds like how long a model's prediction maintains a certain level of combined probabilistic and possibilistic confidence, and the compatibility degree of precisiations, basically. How well different experts' ways of quantifying uncertainty seem to fit together within the model.
This is really mind-expanding. So pre-NNs, especially through these MOE and TKINN ideas, could potentially help us not only model the system we're interested in, but also gain insights into the reliability and consistency of our own understanding of it based on how the expert knowledge interacts.
That's a key potential takeaway, absolutely.
Yeah.
Now, we've spent a lot of time talking about systems where we have some underlying physics or at least some mechanistic understanding that we can describe with equations, even if those descriptions are imprecise, right?
Right, using IDEs.
But what about systems where we really don't have those kinds of governing equations readily available? Think about those complex economic or social systems we mentioned earlier, things driven heavily by human behavior, intricate interactions.
Yeah, systems where the fundamental laws aren't as clear-cut or maybe even known compared to classical physics. How do PRINs help us there?
Well, even without known differential equations, PRINs can still be informed by knowledge. In this case, often by what the research calls perception-based rules.
Perception-based rules.
These are more like the rules of thumb, the expert insights, the heuristics about how the system tends to behave under certain conditions. The key difference from physics laws is that these rules are often more flexible, more elastic, you might say. They're often local, context-dependent, and less universally rigid.
So instead of hard and fast mathematical laws, we're giving the AI a set of more adaptable guidelines based on human experience and observation, like qualitative knowledge.
Exactly. Softer, more human-like understandings. And the research focuses quite a bit on expressing these perception-based rules in the form of fuzzy if-then rules.
Fuzzy logic, okay?
Right, which are then made precise or precisiated using something called the fuzzy graph mode.
Fuzzy graph mode.
Think of a simple fuzzy rule like, if the price of a product is high, then the customer demand tends to be low. Here, high price and low demand aren't precise numbers, but rather fuzzy sets, they represent a range of values with varying degrees of membership or truth.
Right, like very high, somewhat high, etc.
Exactly. The fuzzy graph mode provides a way to mathematically represent the relationship, the constraint, implied by this if-then rule connecting these fuzzy sets.
So the AI isn't looking for an exact price point that triggers a specific demand number, but rather it's learning to understand the general relationship between the fuzzy concept of high price and the fuzzy concept of low demand.
Correct. And when PRINs incorporate these fuzzy graph precisiations derived from fuzzy rules, they become fuzzy-informed neural networks, or FNNs.
FNNs. Okay, another one.
Yes. The overall fuzzy constraint, which might combine multiple such rules, is then integrated into the network's loss function, just like the physics equations were in PNNs. It guides the network's learning.
So it's penalized if it violates these fuzzy rules too much.
Essentially, yes. This marks a really significant shift, moving from traditional, often static, fuzzy, rule-based systems towards data-integrated, trainable fuzzy models within a deep learning context.
And the research gives some great examples of how this could be used, right? Like modeling customer behavior based on fuzzy rules linking, say, time of day and how much they tend to buy.
Exactly. Or describing local changes in a system using perception-based derivatives where the rate of change itself is described fuzzily, like the change is small positive when x is around 0.
Yeah.
Or even capturing economic relationships, like how customer satisfaction may be described as high relates to purchase frequency, perhaps described as frequent.
These examples really showcase the adaptability of FNNs, don't they? Even without precise equations, we can still leverage expert knowledge, expressed as these fuzzy rules, to guide the AI's learning process in really complex, maybe human-centric systems.
Definitely.
And it sounds like these FNNs have some significant advantages over older approaches to fuzzy systems, like maybe AIR and FIS or traditional fuzzy inference systems.
Yeah, the paper highlights several. FNNs are generally more flexible in their architecture. They can be part of deeper networks. They can be trained end-to-end with the rest of the network, rather than requiring separate stages for rule tuning and parameter fitting.
Okay.
And importantly, they often don't require that explicit defuzzification step at the end where you have to convert a fuzzy output back into a single crisp number. The network can learn to produce the desired output directly while still being informed by the fuzzy constraints.
That sounds much more integrated.
It is. SDENs essentially integrate the principles of fuzzy logic directly into the power and flexibility of modern deep learning frameworks. This allows for potentially handling more complex rules, adapting better to data, maybe being more robust to outliers, and even more efficient processing, especially for more advanced types of fuzzy logic.
So it seems like whether we have some understanding of the underlying mechanics of a system that we can express, even imprecisely, maybe as IDEs, or we just have a collection of expert-derived fuzzy rules about how it behaves, PRINs offer a way to bring that knowledge, that perception, directly into the neural network's learning process.
Exactly. That's the core idea. And as we've discussed, the different ways we can choose to precisiate those imprecise perceptions or rules, whether using singular values leading back to pins, or probability distributions like in PINS-U or BPNs, or possibility distributions like FCINNs or FPNs, or fuzzy graphs, FENNs, or combining expert opinions, MOE, leading to things like CINITs or TKINs.
Right, all those acronyms.
All lead to a whole range of specialized informed neural networks. Each is tailored for handling different types of uncertainty and different forms of knowledge or perception.
So instead of just having one way to teach physics or other knowledge to an AI, we now have this whole spectrum of methods, a toolkit, really tailored to different kinds of information.
It's like PRINs are this overarching philosophy, this unifying framework, and all these different specific network types, PINs, FINs, CINETs, TKNNs, MOENs, and the others are different implementations or tools within that larger PRIN toolkit, each designed for a specific type of information and uncertainty.
That's a really helpful way to think about it. PRINs provide a fundamental framework for understanding all these different approaches to building informed AI, and maybe for inspiring the development of even newer techniques down the line.
I think that's the hope, yeah.
So just to kind of wrap up, PRINs represent this really innovative way of building AI that goes beyond just learning from raw data points. They allow us to explicitly incorporate our existing understanding of the world. That understanding could be in the form of physical laws, even imprecise ones.
Right, IDEs.
Or it could be more qualitative, perception-based rules, like fuzzy rules.
Like in FANGLINs.
And crucially, they provide mechanisms to account for the inherent uncertainty in that knowledge and even handle potentially differing viewpoints among experts.
Precisely. And this opens up the really exciting possibility of creating useful models for incredibly complex systems. Systems where traditional physics-based approaches might struggle because we don't know the exact equations, and where purely data-driven methods might need far more data than we can realistically get our hands on.
Yeah, it sounds like PRINANS could be a real game changer across a huge range of fields, from engineering and science to economics, biology, maybe even social sciences.
Absolutely. It feels like a platform for really pushing the boundaries of computational science and modeling. It might allow us to potentially discover new forms of fundamental relationships, maybe new types of differential equations emerging from combined expert knowledge,
Wow.
and just build much more robust and insightful models by intelligently leveraging the power of human expertise and perception alongside data.
Well, this has been a truly fascinating deep dive into perception-informed neural networks. It's amazing to see how AI is evolving.
Yeah.
Seems like it's starting to understand the world in ways that are becoming much more aligned with how we humans actually do it, warts and all,
Yeah.
uncertainty included.
Indeed. It's a very exciting direction. And it leaves us with maybe a final thought for you, the learner, to ponder.
Okay.
Considering how PRINs are opening the door to incorporating these more nuanced forms of human understanding, uncertainty, fuzzy rules, expert disagreement, how might we one day even begin to integrate something perhaps even more subtle, like human intuition, or maybe tacit knowledge that stuff experts know but can't easily articulate into AI models? Could PRINs be a stepping stone towards that?
Integrating intuition, that's definitely something to think about, a fascinating future direction.